Okay, so hope you're all doing good. So in our this lesson, we're just going to be solving this examinable question. Yeah, a question from a past paper. So the question is find d over dx of 2x, 2 to the power x. So basically what it means when they say d over dx. So this just simply denotes that the value here that we are finding is for this. We know that that function 2 to the power x is not defined by this y being equal to 2 to the power x, but it is just independent on its own. So that is the reason why we are saying d over dx and not dy over dx. So here we are just simply differentiating this function 2 to the power x with respect to what? To x. Yeah, we're not differentiating that function as a function of y, but as a function of itself. It's just independent. Yeah, okay, so let's now dive right into it. Okay, so to solve this question, so I posted this question in the WhatsApp group, and then there are people who were solving this question using power rule, where they were saying that okay, let me use a different color. So where they were saying that d over dx of 2 to the power x is simply equal to. So what they were doing is they get the x, that value of x, multiplied it by the 2, which is that one. And then they were having something like x multiplied by the 2 and to the power x, then they subtracted the 1 like this. Then they said the final answer is something like 2 to the power x of x, rather here is supposed to be minus 1. So this was their answer, which is totally wrong. So here we're not going to apply power rule. So what we are having here, it is a function which is raised to a certain variable. So when you have been given a function and it has been raised to a certain variable, what you usually do is you apply differentiation by implicity, differentiation by logs, and the product rule. So we are going to see how all these are going to apply just on this one question. And I think you're going to get everything here just from this question. Okay, so what we do is we know that this function that we've been given, it has been raised to a certain variable, which is x. And then to solve this one, we know, like from semester 1, this power can become the what? The coefficient. We can drop that power and make it become the coefficient like x multiplied by the 2 like this. Now, what rule helps us to do this in math? It is only logs. Logs, yeah. So here we're going to apply logs to this question. Now, what we're going to say is this. So we have d over dx of 2 to the power x. What we're going to do is we're going to introduce the y. So we are going now to say y being equal to 2 to the power x. So what I mean is this. We're going to say d over dx, open bracket, we say y being equal to 2 to the power x. So we haven't changed anything here. We are just doing what? Playing with this function. Yeah. Giving it at least more what? Yeah. More meaning now. So we are just equating this function to y. So we are just saying y being equal to that function. Now all we want is to take that power, which is x, down. So what we can do is we can introduce logs or ln. So if what we're going to do to this part, left hand side part, we are also going to do it to the left hand side part. Yeah. So we introduce ln to the x part and to the y part, left side and to the right side. Okay. So what we're going to do is this: d over, so it's d over dx. Sorry. So open bracket, then ln of what? Of y being equal to ln of what? Of 2 to the power x. So the reason of introducing the ln, it's very simple. We just want you to do what? To drop that power so that we can solve it in a simple way. Yeah, that's it. And you can solve this minus applying the ln to this question. So all questions that have the same expression, they are raised to a certain variable, this is how you go about it. Yeah. So you go about them like this. So ln to the ln y is equal to ln 2 to the power x. Now we can do what? We can drop that power because we have ln here, and then this ln is a log, and logs, they allow us to do what? To make powers become coefficients. Yeah, which is very simple. Okay, so let me solve this on the next page. So we have something like this now. So we have d over dx, then open bracket, a ln of y being equal to ln of 2 to the power x, like that. So now let us drop that power. So we're going to say d over dx of ln y being equal to x ln 2, like this. Very simple. Very simple. I think you're following now step by step. So what we're going to do now is differentiate both sides. Yeah, because here the question was saying we do what? We differentiate the function, and we haven't even started differentiating it, but we're just altering it. Yeah, so now we can differentiate the function. So we differentiate the left hand side part and the right hand side part. So if we differentiate this part, ln y, so mind you, we are differentiating with respect to what? To x. And there we're having what? Y. So this now introduces us to the what? Implicit differentiation. So if we differentiate y, we are going to differentiate it normally the way we do it, like if we have maybe a function to say, okay, if it was a ln x, and then you want to differentiate x, what do? Differentiate it normally. If we differentiate ln x, we're going to have 1 over x. So this is how we differentiate logs. You simply differentiate the function which is in between the log, and then you divide by the same function. So if we differentiate x, we get 1, and divide it by the same function which is x, which is there. Yeah, so these are logs differentiation. Okay, so now here we are having a y here. What are we going to do? So we're going to differentiate it normally. Like, we're just going to assume that, okay, let's differentiate it like the way we do it when we have x. So it will be 1 over what? Over y. But we're going to add something to that answer, which is dy over dx, just to denote that this function was differentiated with respect to x, but we were not having the value of x, or the x function, in that expression. Yeah, so this is how we do it. So what I mean is this: we are going to say here ln x, if we differentiate this part, we're going to have 1 over y, but we're going to add dy over dx. Yeah, like this. Now this is being equal to, if we differentiate this part, now look, here we're having two terms. We're having x and ln 2. So what do we do? So if we have this, we're going to apply now what we call product rule. So product, it is the answer that you get after multiplying two expression or two things. Same as the answer that you get after you subtract two things is called what? Yeah. Hope you know. Same as addition. The sum, the summation of something, the difference. Yeah. Okay. So the product is the answer that you get after multiplying. Okay, and the difference, the answer that you get after subtracting, obviously. Yeah. So now in this case, we're having x and ln 2. So these guys are being multiplied, and what we're going to apply here is product rule. Yeah, and the differentiation. So what we do, so there's actually a formula that we use. So it goes like this. It is v plus u. So it is v plus u, and then you now add here u prime, here v prime. Okay, so what is our v here? You can take anything, or I mean any value to be your v, or any value to be your u. Yeah, but I would just advise maybe you go by the alphabet order. Yeah, we know that here the letter that comes first in the alphabet order is U. So you just take U to be your first term. Yeah. What I mean to be the first term is the number that is coming here in these two are multiplying. Now the value that is coming first between x and ln 2, it is what? It is x. Yeah. So we're going to take x as our what? As our U. And ln 2 as our what? As our v. So the u prime there, it is just denoting that we are supposed to differentiate the same value u that we're going to get as our u, we differentiate it. And then the v, we're also going to do what? To differentiate it. Yeah. So, and then after we do this, the answer, we do what? We take it here. We put it there. Yeah. So this is just the formula for what? Product differentiation. That one. Okay. So let us solve it now using this formula. It is v u plus u v prime. Okay. So I'm going to get this one as my u and this one as my v. Also that formula, you can even write it the way you want it. Maybe we know that addition is commutative. Yeah. So whether I say u v prime plus vu prime, it doesn't matter. You're going to get the same answer. Yeah. The arrangement here doesn't matter. Okay. So I think I'm going just to go by this. Yeah, the second one. Okay. So I'll get my u the way it is, which is x. So this is my u, then this is my v. So my u, I get it the way it is, which is x. I multiplied it by the derivative of the second now, the second function, which is ln 2. This is a log. If we differentiate a log, what do we have? So we differentiate the value that we have in between over the same value. So differentiating the constant gives us a what? A 0. So it is a 0 here over a 2. Now we know that this is not even going to do what? To make sense. So this is obviously a 0. But let's finish it up. So we say plus, we get now the second value, which is our v. Our v here in this case is ln 2. The way it is ln 2 multiplied by the derivative of the first function now. So the first function is our u, which is this one. If we differentiate the x, what are we going to have? Obviously, it's just a 1 without adding dy dx, because we're differentiating this with respect to what? To x, and there we're having a variable of x. Yeah. So now this term has gone. In number multiplied by 0, it is 0. So 0 over 2, it is 0. 0 times x is 0. So we cancel this one. Plus ln 2 multiplied by 1 is what? Ln 2. So the value here that we're having, it is ln 2. Okay. So we get that ln 2 and put it back there in our equation, which is this one here. So it is equal to ln 2. So we have solved this part. The answer is ln 2. Yeah. Hope you are following. Now, all we need is to do what? To find the dy over the x. And this part, we are having dy over dx. So let us make dy over dx the subject. Then we are done. Okay. So here we're having 1 over y dy dx. So what we're going to do is to multiply the whole of this. So we're going to have, so there it's a 2. So we're going to multiply this by y. Why are we multiplying by y? So that y can do what? Multiply with that one, and then we have the expression like y over y, which is 1. This y will cancel, this y will cancel. We will remain with what? Dy over dx. Yeah, like that. Okay, so we are having, so if we multiply this side by that, so left hand side part, we're just remaining with what? Dy over dx. So write it here, dy over dx being equal to, now this part we are also, don't mind, okay, here that was supposed to be y. So this part, right hand side part, if we multiply y times ln 2, we're going to have y ln 2. Okay, so that is an expression that we're going to have dy over dx. So this is dx is equal to y ln 2. Now recall, we had an expression ln 2. So we had an expression at first which was like okay, so let's take note of this one. Dy over dx is equal to ln 2 multiplied by y. Okay, y ln 2. So we are having dy over dx being equal to y ln 2. Now remember, we had a function that was 2 to the power x, and then I said we are going to introduce y. Give respect to this function. We're going to say y is equal to 2 to the power x. 2 to the power x, like that. At first, we had this. Then we introduced the y and equated that y to the what? To the given function that we had, which is 2 to the power x. So meaning y is equal to this, 2 to the power x. And there, in our final answer, we're having what? We're having y. So it's obvious. The value of y, we have it, which is 2 to the power x. What we're just going to do is, where there's y, we put this 2 to the power x. Then we are done. We have solved the question. Very simple and very easy. So we're just going to say dy over dx is equal to, where there's y, I replace it with what? That 2 to the power x ln 2. So this is basically the answer. Yeah, we are done.